Hello, my name is Harsha Kaul, and I am a fourth-year undergraduate student working with Dr. Manel Arando in his astrophysics lab. My project centers around the analysis of Veritas blazar data, specifically working towards a luminosity function of blazars. My project centers around very high energy gamma ray observation. The importance of this observation is that it gives us a better understanding of particle acceleration in extreme environments, which isn't possible on Earth. And this is because we're talking about energies that are much higher than we can recreate right now. Detection is done by using ground-based imaging atmospheric Cherenkov telescopes. And these telescopes afford us a much higher collection area than their spaceborne counterparts, which only have around 1 meter squared, versus a ground-based telescope, which can use the entire atmosphere and have around 10 to the fifth meter squared collection area. And these telescopes detect Cherenkov light that's produced by particle showers, and we'll get into that right now. So TeV gamma ray photons, or just essentially very high energy gamma ray photons, produce particle cascades when they impact the atmosphere. And these cascades produce, in turn, Cherenkov radiation, or Cherenkov light. And this Cherenkov light is basically produced when shower particles move faster than light can in air. And Cherenkov light is visible to the telescopes that we were talking about earlier, the ground-based imaging atmospheric Cherenkov telescopes. However, a problem occurs in that other particles, other than gamma rays, can impact the atmosphere as well and produce Cherenkov light. So particles like relativistic protons and nuclei, which we call cosmic rays, can impact the atmosphere and can confuse us because we can't understand which one is a gamma ray versus which one is just a relativistic proton or nuclei or a cosmic ray. And so imaging atmospheric Cherenkov telescopes have to distinguish between these cosmic ray background and the desired gamma ray photons. And they do that through various software and analysis procedures. The specific IACT we use in our lab is the Veritas array, which is an array of 4 ground-based IACTs that each have a 12-meter optical reflector, and it's based in Arizona. These IACTs, as we said earlier, detect Cherenkov light from cosmic and gamma rays, and they're one of 4 major ground-based IACT arrays around the world. So the specific TeV gamma ray sources that we look at through Veritas are usually active galactic nuclei. And active galactic nuclei are basically compact nuclei that outshine the rest of the galaxy. So they're very, very bright, and they're thought to be powered by supermassive black holes in most cases. And these AGNs emit non-thermal radiation across the entire electromagnetic spectrum, including the gamma ray spectrum. In my project, we are specifically interested in studying blazars, which are just an interesting class of AGN that have relativistic jets pointing towards the observer. And these blazars emit gamma rays that we can view from millions and billions of light years away and all the way on our own planet through these IACTs and this Cherenkov light. So how did my analysis occur? Basically, I use a software package called Event Display, which is a Linux-based software package to examine Veritas data. And Veritas is examining 36 blazar sources. And I decided to start with the first 15 low energy sources because they had smaller data sets and they'd be a little bit easier to handle, and I could make my analysis pipeline a little bit more streamlined. So my analysis pipeline was essentially to take data from Veritas using their website and their computers and import it to our lab computer, then use a data selection algorithm to select the quality data, and then combine that data to give an overview of our detection of the object. So my project's results are a little bit confusing to understand if you're not familiar with astrophysics. So essentially, I'd like to point your attention towards the 4 highlighted sources here and their sigma values. So sigma is a marker of significance. And essentially, if you have a 3 sigma or greater significance for an object, you have a strong likelihood of the object having actually been detected. Because if you remember back to earlier in the presentation, I talked about how it's hard to differentiate between the cosmic ray background and the actual gamma rays from our sources. So the sigma gives us a significance value for how likely it is that the source that we are observing is actually a source and not just cosmic rays that are interfering with our analysis. And so it's really exciting that 4 of these lower energy sources have 3 sigma or higher detections. And 5 sigma or higher is a pretty good baseline for that source is definitely there. Another important part of my results is that we were able to calculate approximately how much time it would take to detect at 3 sigma or 5 sigma each of these sources. And around 8 of these sources have the potential of being detected at this higher sigma or significance value with less than 25 hours more of Veritas observation. And so we'll get into the importance of this right now. Basically, as I said, 4 sources with significant detections, and you can see those back on the recording if you'd like. And so what's the importance of all this? Well, Veritas observation selection for this year is going on in the next week or two. And Veritas, as a telescope, has a very limited observational capacity each year. And this is reasonable considering that you can only point the telescope towards one area of the sky at a time. And you can only use that finite amount of time to look at certain sources. So scientists need to be able to maximize the benefit they'll get out of observing a source while minimizing the amount of time they have to do it. And so if we go back to the previous slide, you can see that some of these sources at the bottom here, for instance, RGB J1037 plus 571, to get to a 3 sigma detection, it would take 116,000 hours, according to our analysis of the data so far, to get to a 3 sigma detection. And that's ridiculous. Veritas can't do that, or it could, but it would be a much less efficient use of its time than, say, doing another 20 hours of observation on RGB J1838 plus 480 and getting to a 3 sigma detection there. So object selection is very important to maximize the benefit of the observation. And we will likely take a closer look at the above 4 sources here that I've mentioned with the significant detection due to unexpected high significance values, but we'll also likely look at the other sources that take a smaller amount of time to get to 3 or 5 sigma significance. And so the next steps for me are mainly continuing the analysis of the remaining 21 objects in the group of blazars, and then sharing my results and improving the analysis chain so that we can streamline it even further and work even more efficiently. That's all. Thank you for listening.